Hello and welcome to section 11.6, which is areas of regular polygons. So what we're going to be doing today is finding the area of polygons that are regular. So let's begin by figuring out or reminding ourselves, what is a regular polygon? Well, a regular polygon means that it's convex, meaning it doesn't cave in on itself. It's equilateral, meaning all of its sides are congruent. And it's also equiangular, which means all of its angles are congruent. So here we have triangle through decagon. So for all of these regular polygons, all sides would be congruent and all of their angles would be congruent. So for this first example, we're actually not going to be finding the area of a regular polygon, but we're going to be talking about angle measurements, which is really important to later be able to find areas of regular polygons. Now in this diagram, we are told that ABCDE is a regular pentagon inscribed in circle F. We are going to find each of the following angle measures. The first one that they want me to find is angle AFB. So notice that is this angle right here. Now notice that that top angle is, well, I call it the top angle of this triangle here, ABF. So what I'm going to do is I'm going to create a bunch of other triangles that start from F and go to the vertices of the polygon. Now all of these sides are congruent. That's what makes this a regular pentagon, and then these sides are all congruent as well because notice that they are radii of the circle. So these 5 triangles that I've drawn in are all congruent. So to find this angle, I know it's going to be congruent to this one, congruent to this one, congruent to this one, and congruent to this one. If I put those all together, line them up the way they are, notice that they form a circle. And the degree measure of a circle is 360 degrees. So I know that the sum of those 5 angles is 360. To get each individual one, I would divide by 5 because I have 5 of those angles. This would give me a value of 72 degrees. Now if I wasn't sure if that's right or not, I would take 72, multiply by 5, and I should definitely get 360. The next angle here that I'm asked to find is angle AFG. So notice that that angle is formed right here, AFG. Because the whole red triangle is isosceles, when I drop down that altitude, it's also an angle bisector, so I would have to bisect that entire top angle, which I call top angle AFB, which we found was 72, and divide that by 2. That's 83. Okay, divided by 2, and we get 36 degrees. The last angle that we're asked to find here is angle GAF. So that is this angle right here, the bottom angle of this little right triangle. So again, notice that it is a right triangle. So the way that I'm going to find that angle, I have that there's a right triangle. I have that little blue one that I found in the step above. It's 76, and then I'm looking for the green one. So what I'm going to do is the angles of a triangle add up to 180. So I take 180 minus 90, because it's a right triangle, so it took up 90 degrees, minus that blue angle, 36, and I would get a value of 54 degrees. All right, so keep in mind this angle and this angle plus 90 should add up to 180. They do, so I know I did this correctly. All right, next up, let's define some words that we're going to use quite a bit in this section. The first one is center, and we're talking about the center of the polygon. And in this picture, we're going to refer to the same pentagon from example 1, the center of the polygon. And in our case, it is the point F. The radius of the polygon is a segment that connects the center to a vertex of the polygon. Okay, so if I take this picture and I look for those segments from the center, point F, to any vertex. So we have 5 vertices because it is a pentagon. So I have 5 radiuses or radii here. So they would be FA, FB, FC, FD, and FE. It's a pentagon, so it should have 5 radii. If it was an octagon, it would have 8. If it was a triangle, it would have 3. and so on and so forth. Okay, the next word is probably something you've never heard before. It's an apothem, or some people call it an apothem. It just depends who you ask. And what that is, it's the height of the triangles in the polygon. So remember from before when we were finding angles, I drew all these little triangles within the pentagon, and one of the apothems was already drawn. It's from F to G, because remember that the height of a triangle is always along a perpendicular, so it has to be perpendicular. Don't forget that. Now earlier when looking for the angle measures, I drew that segment FG in blue. This would also be right here an apothem, this would be an apothem, this would be an apothem, and because these triangles are all congruent, all those segments are also the same length. Okay, the central angle is the angle at the top of the triangles that I drew. So in the angles that we found up top, it would be angle AFB, because it starts at the center and goes vertex to vertex. So it goes to points on the circle. Remember we talked about central angles last chapter. It's formed with the center of the circle, and then its endpoints are on the circle. So we have that central angle, this central angle, from F to D, from F to E. Those are all, these angles up here would all be central angles. Okay, so that brings us to our first real example of finding the area of a regular polygon. So the first thing we're going to do here is read how many sides our shape has. And so we're finding the area of a regular hexagon, which has a side length of 3 meters. Hexagon, the X in it, remember that has an X just like the number 6, so we have a 6-sided regular polygon. So I'm going to go ahead and try to draw a hexagon as best as I can, and not great. Now they told me it has a side length of 3 meters, so I know each side, because this is regular, has a measure of 3 meters. The way that we're going to be finding areas of these regular polygons is we're going to be splitting them into triangles. So from the center to each of the vertices, I'm going to draw on both of those radii, and I'm going to create these little right triangles every single time. So here are the steps that we're going to follow. Step 1, find the central angle of that triangle. In our case, so it's always going to be 360, and then you divide by the number of sides your polygon has. We have a hexagon, so we divide by 6. That gives me an angle of 60 degrees. But what I want to do really is to find the area of this. Ultimately, what I want to do is find the area of this little right triangle. So what I'm going to do for step 2 is I'm going to take that angle. So take the angle found in 1, or number 1, and divide by 2. Right? And the reason I do that is that now gives me, if I take 60 and divide by 2, I now have this information about my little right triangle. This angle, this top angle, will be 30 degrees in my example. Now I need to find this leg. And if this entire side is 3, I divide it by 2, I get 1.5. Okay, remember that my ultimate goal here is to find the area of this little right triangle. To find the area of any triangle, what you need is the base and its height. Now I have the base, I don't have the height. However, I do notice it's a special right triangle, and because 30 degrees is this top angle and I have the side across from it, I have the short leg. So the long leg, which happens to be my height, is 1.5 and then square root of 3. Okay, so that gives me the information that I need to find the area of this little right triangle. So it's 1/2 the base, which is 1.5, times the height, which is 1.5 root 3. This gives me a value of 1.125 square roots of 3. But remember, what I'm supposed to find here is not the area of a little right triangle. I'm supposed to find the area of a regular hexagon with a side length of 3 meters. So if I have the area of this little right triangle, I have to figure out how many of those little right triangles make up this hexagon, and then I would just multiply by that number of triangles. So notice if I was to split each of those isosceles triangles that go to the vertices, if I split them in two, I have 12 of them. So what I'm going to do is take this area and multiply it by 12. So 12 times 1.125 square root of 3. And it gives me the area of my regular polygon, which is about 23.23 meters squared. And I should have given the exact answer first. Sorry, it's 13.5 square roots of 3, because I would do 12 times 1.125 and then bring along that square root of 3. Okay, so next example here, we want to calculate the area of the regular polygon below. Notice that they drew my right triangle for me. So I'm going to go ahead and redraw it a little bit bigger. I have the height of it is 6.5, and I have that the hypotenuse is 8. So what I'm missing is this base. Because remember, my goal is to find the area of that little right triangle and then multiply it by how many of those little right triangles would fit in the polygon that I'm looking for the area of. So to find the area of a triangle, you need its base and its height. I have the height, I don't have the base, but I do have a hypotenuse. So in this case, I can use Pythagorean theorem to find the missing side. So x squared plus 6.5 squared is going to equal 8 squared. So 42.25 plus x squared equals 64. Subtract 42.25, you get x squared is equal to 21.75. So x is approximately 4.66. All right, that gives me then enough information where I could find the area of one of these little triangles. So the area of one triangle is 1/2. The base, which we just found, is 4.66 times the height, which is 6.5. This gives me an area of 15.145. Okay, so let's recall that my original plan here was to find the area of the original polygon. Now it is a pentagon, it has 5 sides, so I split it up into triangles, and then within those triangles I have these little right triangles. So how many would there be? There would be 10. Now, in case you haven't figured out, the number of triangles is always twice the number of sides of your polygon. So our previous example where we had a hexagon, there was 12 of them. Now we have a pentagon, there's going to be 10. So the area of 10 of these triangles is going to be 10 times 15.145. That gives me a grand total of, let's see, 151.45, and then I have no units, so I'm just going to call it units squared. So in these problems, to find the apothem, the radius, or side length, there are going to be 3 possible methods that you're going to be able to use. So we've already used 2 of them. The first one was with example 2, our hexagon. To find a missing side length, we use special right triangles. So that's one of our ways. So that's our 30, 60, 90s, or our 45, 45, 90 degree triangles. The second way we found a missing side length was in the previous example, example 3, and that was by using the Pythagorean theorem. And the last way, which we haven't used yet, but we are going to use quite a bit in this section, is trigonometry. Better known as SOHCAHTOA. Alright, so example number 4 here says find the area of a square with a radius of 6 centimeters. So we're going to draw our square. And then I'm going to inscribe this inside of a circle. I'm going to circumscribe a circle around it. Oh, that was not too bad. Okay, so if the radius is 6 centimeters, that means it goes from the center to a vertex. That's my length of 6 centimeters. So as always, I'm going to draw my little right triangle. And this is what my focus is going to be on until I have to multiply at the end by how many of these I would have. All right, so if you're only given one side length, what you have to do is find that top angle. And again, before I gave you the steps, we're going to find the central angle. And the central angle would be 360 divided by 4. Because remember, that's those triangles that are formed this way. 1, 2, 3, and 4 of them. They form those top angles form a circle when they come together. So that's 360 divided by 4 is 90 degrees. And then I take that angle and I divide by 2 to get a 45-degree angle. So let's redraw our right triangle, making it a little bit bigger so we see what we're dealing with here. We have a 45-degree angle there, and we have a hypotenuse of 6. Remember that in 45, 45, 90-degree triangles, the hypotenuse is equal to the leg times the square root of 2. So I'm going to plug in, my legs are congruent, so it doesn't matter which one I'm looking for. The hypotenuse I'm given here is 6. The leg we don't know, let's call it x, and then we divide or multiply by square root of 2. To get x by itself, divide both sides by the square root of 2. You don't have to simplify for these problems because it's all going to kind of cancel nicely anyway. So it's x is equal to 6 divided by the square root of 2. Alright, so the nice thing about this triangle then is if I find one of the legs, I have the other legs, and in a right triangle the legs are both the base and the height, so I can go ahead and find the area of one triangle. It is going to be 1/2 the base, which is 6 divided by square root of 2, times the height, which is also 6 divided by the square root of 2. Now you can cancel if you want, so 2 goes into 6, or you could go ahead and multiply all the numerators together. You would get 1 times 6 times 6 is 36, over 2 times the square root of 2 times the square root of 2 is going to be 2 times the square root of 4. The square root of 4 is just another way to write 2, so that is 4, giving me an area of 9. Another way, I'm going to simplify this a different way, because I would not do it this way where I'd multiply numerators, denominators. I would cross cancel this way. 2 goes into 6, and I only cancel it once, and then I would multiply the numerators together. I would get 1 times 3 times 6 is 18, divided by this 2 went in there once, so 1 square root of 2 times square root of 2 is the square root of 4. You get 18 over 2, which gives you 9. So both of those ways gives you the same answer. I prefer the way that I did this in red. I don't know why it really didn't take any less steps, but I just do it that way. Okay, so now how many of these triangles would we have? Now if you remember, I said if it's a 4-sided figure, which a square is, we're going to have twice as many right triangles. So I'm going to do 8 triangles. So the area of one triangle is 9. We have 8 of them. So the grand total is 72, and my units are centimeters squared. All right, last example here. We are finding the area of an octagon with an apothem of 8 inches. Now, I don't even pretend to try to draw an octagon where I'm going to be able to do all those sides. What I do is I concentrate on one triangle. I know it's going to continue. There's going to be more. I picture it in my head, but I'm not going to be able to draw it. So let's fill in what we know. We know that the apothem is 8 inches. All right, for example 3, sorry I had to add a new page for myself because I drew too big on the other side. But what we're doing for example 5 is we're finding the area of a regular octagon that has an apothem of 8 inches. So let's try to draw an octagon. 1, 2, 3, 4, 5, 6, 7, 8. Awful. But remember, I'm focusing on just one triangle here. And if they gave me the apothem, if you remember from the other side, that is the height of one of the little right triangles. Okay, so here I have that this is 8 inches long. My goal here is to find the area of one of these triangles. So the area of a triangle is 1/2 the base, which I don't have, times the height, which I know is 8. I'm then going to go ahead and multiply that by, because it's an octagon, whatever that area is that I get, I'm going to go and multiply it by 16. So when you're given only one side, the first thing you have to do is find that top angle. So this top angle here is going to be 360 divided by, now I could do divided by 8 divided by 2, or I could kill two birds with one stone, which does sound very violent. I could eat two crackers at one time, I don't know. But I could do 360 divided by the total number of these right triangles, which is going to be 16. That gives me an angle of 22.5 degrees. So redrawing this right triangle, I have the height is 8, and I have this angle here, this top angle is 22.5. What I need is the base, which would be this bottom side. Let's call it x. So in order to find the area of this triangle and to find x, I have to use that third method, which was trigonometry. Now with respect to this angle, x would be the opposite side, a would be the adjacent side, so I'm going to use tangent. So the tangent of 22.5 is equal to opposite x over 8, which is the adjacent. We're going to put that over 1 because we're going to cross multiply. That would give me, multiplying this way, x is equal to, when I multiply this way, 8 times the tangent of 22.5 degrees. This is the base, the little base of the triangle. That's how long it is. It's 8 times the tangent of 22.5. Notice that's what I needed here to find the area of one little triangle. So what I want is for you guys to finish this problem on your own. Remember, when you find the area of this one triangle, that's not enough. What you're doing then is only finding this area. So when you find that, make sure you know how many triangles would make up this octagon, and that's going to be part of the thing I'm going to be checking tomorrow when I check in your notes to make sure you finish this problem. Okay, that's all. Thank you very much for watching and have a great day. Bye.